So our next speaker is Jelle Voss. He is a PhD student at Delft University of Technology, and his talk today is going to be on anomaly detection.
Yep. Thank you very much. Privacy preserving membership queries. This is the ML session, so there might be not too much ML, but I saved that for the end of the talk. So if you're like missing out on that, then it will be there. It will just be at the end. So this was a work that we did with many students and 3 professors. So it was me, Sika, Steven, Ricardo, and Dean, and then Zeki, who might be in the audience, and Martine and Anderson were our professors. So it was a joint work because this is actually a work that was a submission to a competition. And it was the UK-US Bets Prize Challenge. Has anyone heard of that one before? Yeah, so it's basically, it was a collaboration between the US and the UK governments, and they proposed 2 use cases that people could work on. And so we chose the combating financial fraud use case. So in this use case, you have a couple of banks and a payment network service. So this payment network service is there to route the payments between the banks, and the banks really just only send transactions. This is a very, it's immediately like a federated setting because there are 2 types of data here and they're stored in different places. So the banks, they know their customers. So they have customer data. They have account numbers. They have, they know the name of the customers, their addresses, etc. On the other hand, you have the payment network service who has a very global overview of what's happening in the system. So they have all the transaction data, like they know the timestamps, they know where things are going, and also between multiple banks. In this case, it's the payment network service's responsibility to do fraud detection. And you can tell that it's a little bit hard because they don't really know their customer. They just see the transactions. And so the question that was asked in this competition is, can we improve fraud detection by incorporating the bank's knowledge somehow? So there's a very easy way to do it, and that's to just send the data to the other side. So thanks for coming to my talk. This is not how we solve the problem, because there's a very clear problem with that. We don't actually want the payment network service to know all this private information. So they're not allowed to know the customers, but they somehow have to check for validity. So there's a very important asterisk, so without compromising the user's privacy. So I first want to present sort of our high-level solution. And when I say ours, this solution was almost used by all the teams in the competition. So it's not necessarily ours, but I guess the way that we fill in this box is very different. And then different teams had sort of different security guarantees that they could offer in the end. So there is this kind of closed box, and what it does is it takes in a transaction, and in the end it will spit out a flag that it's like a Boolean that says whether the transaction is valid or not. And valid here means that it's consistent with the bank's data. And also in this box, we also have the sending bank and the receiving bank somehow interacting with it. So the way that all the teams went about this is basically we take the parts of the transaction that refer to the sender, we take the parts that refer to the receiver, and then we basically check if the data is consistent with the respective banks. The result will be yes or no, and then finally we only output that the transaction is valid if both are indeed correct. So a candidate solution for this is to use multi-party private sender sections. Like it feels like there are already very good tools to do so. So let's look at what happens when you do that. So now you'll be doing not one transaction every time, but you can sort of batch together multiple transactions. So you'll input many transactions and get out the list of valid transactions, the subset of valid transactions. And so this would be the MPSI. So you are checking whether all are in the set. There are a few drawbacks to this, and I'll show them later in more detail. But a big problem is that each query here requires a lot of bandwidth. Basically, the bandwidth scales somehow with the entire set of data that the bank stores. So even if you perform a single query, you basically have to expend all this bandwidth every single time. So putting that in a larger overview, what we have is a solution that barely has any setup happening between the banks and the payment network service. But for each query, we have like a huge amount of compute and bandwidth consumed, even for a single check or like a single transaction. So what do we want? We want to, probably expend a lot of effort in this setup so that our queries are super, super cheap to compute and basically just scale with the size of the transaction. So we call this thing on the left a parallel membership query, and on the right a repeated membership query. And so this is what we propose. Like I think we are the first to propose repeated membership queries. So where you have the same data set that, for example, doesn't change apart from on a daily basis, and then those queries are super, super fast to compute. The key to our solution is a new kind of abstraction that we call encrypted membership query filters. And it's basically like this. So there are two methods. One is encode. So it takes some kind of set and it encodes it into an EMQF. And very important here is that it doesn't leak the data set of whatever you are inputting. So the EMQF literally just looks like random data. And then there's also a decode function. So it takes the EMQF and it takes some query, and it returns an encryption of 0 if that query is in the data set, and otherwise an encryption of randomness. Now this is a very common thing in, for example, multi-party private set intersections. But this specific abstraction has not really been shown before. But what's interesting is there are many different ways to instantiate it, and these have been shown before. So encrypted polynomials is one way. You can show that these are optimal in size, but they're very slow to encode and decode. So in practice, they're not really great to use, especially like knowing that the bank's data set is pretty big, right? So it doesn't scale very well. And then there are encrypted Bloom filters. I've worked on these in the past. They're kind of nice, like they're fast to encode and decode, but they are approximate. And actually, there are very subtle security problems with it. And then, so some people in the audience might be aware of this, there are oblivious key value stores. And so oblivious key value stores in many ways resemble already an encrypted membership query filter. Basically what this is it's a key value store, but the values that it stores are supposed to look very random. And because they look so random, you can, the final structure also looks random. So these are somewhat fast to encode, but they're really, really fast to decode. So these are very convenient. And these are being used in the latest MPSI protocols too. So our solution using EMQFs looks as follows. So this is just the previous high-level overview. And then what we do is we basically have the sending bank and the receiving bank encode their data set as an EMQF and send that to the payment network service. So this happens just once during the setup phase. And then a transaction is split into the relevant data for the sender and for the receiver, and those are, the EMQFs are queried on that data. Then the output is an encryption of yes or no, and we perform an AND operation. And the way we really go about it is that it's a partially homomorphic encryption of 0 or randomness, and we add up this result. So the result is still 0 or random. So it's still 0 if both are in the EMQFs. So both transactions, both parts of the transaction are considered valid. In the end, we decrypt, but we also randomize, because if you would query on the EMQF with the same query, you'd get the same result. So you need to somehow re-randomize that, so that when you send stuff to the banks, that the banks don't know what you've been querying on. Now, I saved all the interesting cryptography for just one slide. So if you don't care about the cryptography, you can close your eyes right now. So the key idea here was to, we wanted to make it really fast and really compact, because there are so many transactions that need to be sent to the other side. And so the key idea is to encode elliptic curve-based Algol ciphertext in such an EMQF. Elliptic curve-based because they're really fast and very compact. And so we found that oblivious key value stores provide the best trade-offs. And what's actually interesting to see is that if you use, for example, those encrypted polynomials, the protocol basically reduces to some previous work from Hazé et al. And then if you use the encrypted Bloom filters, it also reduces to another work. So OKVSs, they're new. Now, they require the ciphertext to be indistinguishable from random bit strings, and we achieve this by using an alligator map. Finally, this is an optimization that we don't really care care about. So our final solution looks as follows. So here's where the ML comes in. So this is the overview we saw in the beginning. We have the EMQFs that are generated on the bank side, and those are sent to the PNS. Then for a query, the PNS queries the relevant EMQFs. The relevant banks perform collective randomization, so each contributes their own randomness. And then there is collective decryption. So the PNS obtains the valid transaction flag. The banks do not get this information. And then some kind of regression is performed. So how does that happen? Well, these are the initial features that we get in this system. And we engineered a few features. So this is basically what we did for the competition. So there's one flag which is, does the currency match, like the instructed currency match the settlement currency? What is the time between the transaction was submitted and the settlement timestamp? And then there's our cryptographic protocol to obtain this single bit of information, which is whether it's a valid transaction according to the banks. And then we perform some kind of differentially private regression model, and we get a risk score out. Differentially private because we don't want the results of this model to reveal anything about the data it was trained on. So these are the results. So we tried a random forest and linear regression. And then the ones where we say EMQF is where we also incorporate our Boolean feature. Okay. So very quickly, this is the overview. The linear regression is, in the end, the solution that we stuck with. And it was trained using DPSGD. And as you can tell, the EMQF solution does actually work. So the Boolean feature does actually provide better accuracy to the system. So in the end, we won the second place in the PETS Prize Challenge. But from the top 3 solutions, I think our solution does have the highest security guarantees, but there's some kind of trade-off there. So we proposed a protocol for repeated membership queries. We provided this nice I think it's a nice abstraction, encrypted membership query filters, and then we provided the first implementation of OKAVSs, where we actually put like ciphertext in there instead of secret shares. Thank you very much.
All right. I'll just ask a short or very long question. We'll see. So I was wondering, you said that you added in the differential privacy to ensure nothing could be learned about the training data. I was wondering what you did to verify that.
Yeah, we didn't. So basically this was, the reason why we didn't is that the competition didn't really ask for it. So I know it's not a satisfying answer, but I would say that our main contribution is this, private membership query, and then the competition just asked for it, and this is what we did. So the competition basically said, these are a few different epsilon values on which we're going to evaluate your solution, and then they said, but instead of using epsilon, if you can't do like epsilon differential privacy, you can also give a bound on the advantage on a membership inference attack. I don't think anyone went with that because it's really hard to do.
All right. We can take one more question if there's one in the audience.
Hello. Thank you for the presentation. So it is not really a machine learning question, but rather a question about your implementation of OKVS over the elliptic curve. So can you elaborate a little bit more about that?
Yeah, I agree. Like that's the interesting cryptography part. But yeah, the key behind making an OKVS secure is that the values that you encode in them need to be uniformly random bit strings, right? And so the problem with elliptic curves is that the curve points do not look like uniformly random bit strings. So you somehow need to mold it into a set of bit strings that look just fine. And it's what's good for us is that people have looked at that problem before. And so one solution is the alligator map. So that works for a couple of specific elliptic curves, and we decided to use exactly such an elliptic curve. So what it does is it takes a compressed curve point and then somehow spits out a random looking bit string, and it's also invertible. It only works for half of the points, so you have to do some kind of rejection sampling, but for us that's no problem. And so then in the end you obtain the same security guarantees that you get when encoding like secret shares into the OKVS. Yeah.
All right, as the next speaker comes down, let's thank this one.